Hello there, and welcome to Theories Before Sleep. I'm so glad you're here. Maybe it's been a long day spent beneath these same stars, though you couldn't see them through daylight. Perhaps your mind is still racing with earthly concerns, tasks left undone, worries that feel heavy. Or maybe you're simply curious about stars, seeking something peaceful to carry you into sleep, something vast enough to make your troubles feel small. Tonight's journey is for you. You don't need to do anything but rest. Let your breath slow, your thoughts soften, and your body grow light. We're going to explore 100 theories about stars and their secrets, not in a rush, but slowly, gently. From how stars are born to how they die, from the light they give to the mysteries they keep, each theory a quiet doorway into wonder. Some will feel familiar, others strange. All are presented to help you drift peacefully towards sleep. If these explorations help you unwind, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. The first theory is waiting, patient and quiet. Stars form in collapsing clouds of gas and dust. Stars begin their lives in vast molecular clouds, regions of space so cold and dark they're called stellar nurseries. These clouds, made mostly of hydrogen with traces of helium and dust, can span hundreds of light years across, drifting through the galaxy like cosmic fog. Something disturbs the cloud, perhaps a nearby supernova's shockwave or the gravitational pull of passing stars, and regions within it begin to collapse. As the cloud collapses, it fragments into smaller clumps, each one pulling itself inward under its own gravity. The centre of each clump grows denser and hotter, atoms pressing closer together, friction building as matter falls inward. Eventually, when the core reaches about 10 million degrees, hydrogen atoms begin fusing into helium and light bursts forth. A star is born. This process takes millions of years, invisible to us, happening in darkness, until suddenly there is light where there was none before, a new point of brilliance in the endless night. Nuclear fusion powers every star's light. The light you see from stars, whether our sun or distant points in the night sky, comes from nuclear fusion happening deep in their cores. At temperatures reaching millions of degrees, hydrogen atoms move so fast they overcome their natural repulsion and collide with enough force to merge, forming helium. This fusion releases tremendous energy in the form of light and heat, radiation that pushes outward against gravity's inward pull. The balance between these two forces, radiation pressure and gravitational collapse, determines a star's size and stability. Our Sun fuses about 600 million tons of hydrogen every second, converting 4 million tons of matter into pure energy, according to Einstein's equation. This has continued for nearly 5 billion years, and will continue for 5 billion more. The light reaching your eyes tonight left those fusion reactions 8 minutes ago, travelling across space at the speed of light, carrying warmth and brightness from a process that turns mass into radiance, matter into morning. Stars are classified by temperature and colour. Not all stars shine the same way, and astronomers have organised them into a sequence based on their surface temperature and the colour of light they emit. The hottest stars glow blue-white, their surfaces exceeding 30,000 degrees, burning through their fuel quickly and living fast, brilliant lives. Cooler stars appear orange or red, their surfaces only a few thousand degrees, sipping their hydrogen slowly and living for trillions of years. Our Sun falls in the middle, a yellow-white star of moderate temperature and moderate lifespan. This classification system, developed over a century ago, uses letters that seem random, O, B, A, F, G, K, M, arranged from hottest to coolest. Each letter represents a range of temperatures and spectral characteristics, patterns in the light that reveal what elements exist in the star's atmosphere. When you look up at night, the colours are subtle but real, some stars slightly blue, others distinctly red, each hue telling you something about that distant sun's temperature, age, and fate. The Hertzsprung-Russell diagram maps stellar evolution. In the early 20th century, two astronomers independently discovered a pattern when they plotted stars' brightness against their temperature. Most stars fell along a diagonal band called the main sequence, where our Sun resides, fusing hydrogen steadily in their cores. But some stars appeared in other regions of the diagram, giants and supergiants far brighter than their temperature suggested, and white dwarfs far dimmer. This chart, now called the Hertzsprung-Russell diagram, became a map of stellar evolution, showing not where stars are in space, but where they are in their lives. A star spends most of its existence on the main sequence, then moves to other regions as it ages, swelling into a giant or collapsing into a dwarf. The diagram reveals that stars follow predictable paths through their lifetimes, paths determined by their mass, and that the night sky is filled with stars at every stage of this journey, from newborns to ancients, all shining simultaneously in the darkness. Stellar mass determines a star's entire life story. The single most important property of a star, the factor that determines almost everything about its existence, is how much mass it contains when it forms. A star with just 8% the mass of our Sun will burn so slowly it could live for trillions of years, far longer than the current age of the universe. A star with 50 times our Sun's mass will exhaust its fuel in just a few million years, dying young in a catastrophic explosion. Mass determines temperature, brightness, colour, lifespan, and ultimate fate. Heavier stars burn hotter and brighter, racing through their hydrogen reserves, while smaller stars glow dimly and endure. This relationship means the universe is full of ancient red dwarfs that formed billions of years ago and still have eons ahead, while the brightest stars you see tonight are relatively young, born perhaps when dinosaurs walked Earth, and will die long before our Sun does, leaving behind exotic remnants in the cosmic dark. Stars spend most of their lives in equilibrium. For the vast majority of a star's existence, it maintains a delicate balance between two opposing forces, neither winning, neither losing, just holding each other at bay. Gravity pulls everything inward, trying to collapse the star into an ever denser point. Radiation pressure from fusion in the core pushes outward, trying to expand the star into the surrounding space. These forces balance perfectly, and the star remains stable, neither growing nor shrinking, shining steadily for millions or billions of years. This equilibrium is called hydrostatic equilibrium, and it's what makes stars so reliable, so predictable in their behaviour. Our Sun has maintained this balance for nearly 5 billion years, and will continue for 5 billion more, a testament to the precision of physical laws. When you see a star in the night sky, you're seeing this balance made visible, light emerging from a battle between forces that neither side can win, creating stability from opposition, constancy from conflict, peace from the tension of equal strengths. Red giant stars represent an aging phase. When a star like our Sun exhausts the hydrogen in its core, fusion stops, and the core begins to contract under gravity's pull. This contraction heats the surrounding shell of hydrogen, which begins fusing instead, releasing even more energy than before. The outer layers of the star, receiving this increased energy, expand dramatically, swelling to hundreds of times their original size. The star becomes a red giant, its surface cooling as it spreads out, but its total luminosity increasing enormously. Our Sun will eventually swell beyond Earth's orbit, engulfing the inner planets, though this won't happen for another 5 billion years. Red giants are common in the night sky, stars like Betelgeuse and Arcturus, visible even to the naked eye, their ruddy colour distinguishing them from younger stars. This phase is relatively brief in cosmic terms, lasting only a few 100 million years, a moment of dramatic change between the long stability of youth and whatever comes next. A transition written in light. White dwarfs, are the remnants of sun-like stars. When a star like our Sun finally exhausts all its nuclear fuel, having fused hydrogen and helium as far as its mass allows, it sheds its outer layers in a gentle exhalation called a planetary nebula. What remains is the core, no longer generating energy through fusion, no longer held up by radiation pressure, collapsing until electron degeneracy pressure stops it. This remnant is called a white dwarf, an object about the size of Earth, but containing roughly the mass of the Sun, so dense that a teaspoon would weigh tons. White dwarfs shine not from fusion but from residual heat, gradually cooling over billions of years, fading from white to yellow to red, to eventually, in the far future, becoming black dwarfs, cold and dark. Our Sun will become a white dwarf someday, a quiet ending to a long life, no explosion, no drama, just a slow fade into darkness, the core of what once was a star, cooling in the endless night, a monument to stability that outlasted its own light. Supernovae mark the deaths of massive stars. Stars much more massive than our Sun die differently, not with a whimper, but with one of the most violent events in the universe. When a massive star exhausts its fuel, its core collapses catastrophically in less than a second, and the outer layers rebound in a shockwave that tears the star apart. This explosion, called a supernova, can briefly outshine an entire galaxy, releasing more energy in a few weeks than our Sun will produce in its entire lifetime. The explosion scatters the star's material across space, enriching the interstellar medium with heavy elements forged in the star's core and in the explosion itself. These elements, carbon, oxygen, iron, gold, will eventually become part of new stars, new planets, new life. Every atom in your body heavier than hydrogen was created in a star and scattered by such an explosion. Supernovae are rare, occurring perhaps once per century in a galaxy like ours, but their legacy is everywhere, written in the very substance of worlds and beings. Neutron stars are incredibly dense stellar corpses. When a massive star explodes as a supernova, if the remaining core is between about 1.4 and 3 times the mass of the Sun, it collapses into a neutron star, an object so dense that protons and electrons merge into neutrons, and matter achieves densities found nowhere else in the universe except black holes. A neutron star might be only 20 kilometers across, about the size of a city, yet contain more mass than our Sun. A sugar cube-sized piece would weigh as much as all of humanity combined. The gravity at the surface is so intense that the escape velocity approaches half the speed of light. Some neutron stars spin hundreds of times per second, their magnetic fields trillions of times stronger than Earth's, beaming radiation into space like cosmic lighthouses. These are called pulsars, and their regular pulses, timed with millisecond precision, were once thought to be signals from alien civilizations. Instead, they're the remains of stars, compressed to the edge of what matter can withstand, spinning in the darkness, monuments to gravity's final victory over everything except the neutron itself. Black holes form when the most massive stars collapse. If a stellar core remaining after a supernova exceeds about 3 solar masses, not even neutron degeneracy pressure can stop the collapse. The core continues contracting, density increasing without limit until it forms a singularity, a point of infinite density surrounded by an event horizon, a boundary beyond which nothing, not even light, can escape. This is a black hole, the ultimate endpoint of stellar evolution for the most massive stars. The event horizon size depends on the mass, ranging from a few kilometers for stellar mass black holes to billions of kilometers for supermassive black holes at galaxy centers. Despite their fearsome reputation, black holes are simply regions where gravity has become so strong that space-time itself is bent beyond recovery. They don't suck things in any more than a star would. They just possess gravity proportional to their mass. Stellar mass black holes likely number in the millions in our galaxy alone, invisible except when matter falls into them, heating up and emitting X-rays in its final moments before crossing the event horizon and disappearing forever from the observable universe. Stars generate heavy elements through nucleosynthesis. The universe began with only hydrogen, helium, and traces of lithium, the lightest elements, forged in the first minutes after the Big Bang. Every other element, from carbon to iron to gold to uranium, was created inside stars or in stellar explosions. This process, called stellar nucleosynthesis, occurs in layers within massive stars, each layer fusing lighter elements into heavier ones. Hydrogen fuses to helium in the core, then helium to carbon and oxygen, then carbon to neon and magnesium, and so on, building up through the periodic table. Iron is the endpoint of this process, the most stable nucleus, beyond which fusion consumes energy rather than releasing it. Elements heavier than iron are created primarily in supernova explosions or neutron star collisions, where conditions are extreme enough to force nuclei together despite the energy cost. The atoms in your body, the calcium in your bones, the iron in your blood, the oxygen you breathe, were forged in stars that died before our sun was born, scattered across space and eventually incorporated into the cloud that became our solar system, making you, in a very real sense, stardust. Binary star systems are surprisingly common. Many stars, perhaps most, don't exist alone, but in pairs or groups, orbiting a common center of mass. These binary systems form when a collapsing gas cloud fragments into multiple cores, or when stars capture each other gravitationally. The stars in a binary can be close together, orbiting in hours or days, or widely separated, taking thousands of years to complete an orbit. Close binaries can interact dramatically, one star pulling material from its companion, leading to phenomena like novae X-ray binaries and eventually stellar mergers. Eclipsing binaries, where one star passes in front of the other from our perspective, allowed astronomers to determine stellar masses and sizes with precision. Some stars exist in triple or even larger systems, complex gravitational dances that can destabilize over time, ejecting members or causing collisions. When you look at many stars that appear single to the naked eye, telescopes reveal them as pairs, two suns where you saw one, each star with its own light, its own character, bound together by gravity, dancing through the darkness in orbits that may last longer than the current age of the universe. Variable stars change in brightness. Over time, not all stars shine with constant brightness. Some pulsate, swelling and shrinking in regular cycles, their light varying as their surface area and temperature change. These are called variable stars, and they come in many types, each with different causes and periods. Cepheid variables, for example, pulsate with periods ranging from days to months, and their period is directly related to their intrinsic brightness, making them cosmic distance markers, standard candles by which astronomers measure the universe. Other variables change brightness because there are eclipsing binaries, or because they're young and unstable, or because they're old and dying, shedding mass in irregular pulses. Some variables change over hours, others over years, and a few over decades. Observing these changes, tracking them over time, reveals the dynamic nature of stars, that they're not eternal unchanging points but active evolving objects, breathing in and out, flickering like candles in a gentle breeze, each variation telling a story about the star's internal structure, its age, its fate. The main sequence is where stars spend most of their time. When you look at a chart plotting stars by temperature and brightness, most cluster along a diagonal band called the main sequence, running from hot, bright stars in the upper left to cool, dim stars in the lower right. This isn't coincidence, but reflects the fact that stars spend the majority of their lives fusing hydrogen in their cores, a stable phase lasting millions to trillions of years depending on mass. Our Sun is a main sequence star, about halfway through its 10 billion year tenure in this phase. Main sequence stars follow a mass-luminosity relationship, More massive stars are far brighter, burning through their fuel faster, while less massive stars glow dimly and endure. The main sequence represents stability, the long middle age of stellar life, before the dramatic changes of old age begin. When astronomers see a star on the main sequence, they know it's in the prime of life, steadily fusing hydrogen, maintaining equilibrium, shining with the constancy that makes stars reliable markers in the night sky, beacons that will continue largely unchanged for eons to come. Stellar winds carry mass away from stars. Stars don't just shine, they also exhale, constantly losing mass through stellar winds, streams of charged particles flowing outward from their surfaces. Our sun's stellar wind, called the solar wind, carries about 1 million tons of material into space every second, a tiny fraction of its total mass but significant over billions of years. Massive stars have even stronger winds, losing mass much faster, shedding outer layers throughout their lives. These winds shape the space around stars, creating bubbles in the interstellar medium, and carry energy and momentum far beyond the star's visible surface. When stellar winds from multiple stars in a region combine, they can compress surrounding gas and trigger new star formation, making stellar winds not just a loss mechanism but a creative force. The particles in these winds, mostly protons and electrons, stream outward at hundreds of kilometers per second, eventually merging with the thin gas between stars, recycling material, and carrying the star's influence across light years, a continuous exhalation that connects each star to the larger galaxy, making stellar death and stellar birth parts of the same endless cycle. Brown dwarfs are failed stars. Not all attempts to form a star succeed. If a collapsing gas cloud gathers less than about 8% of the sun's mass, it never gets hot enough in the core to sustain hydrogen fusion. These objects, called brown dwarfs, occupy a twilight zone between planets and stars, too massive to be planets, but not massive enough to shine through fusion. They do glow with infrared light from residual heat and from the fusion of deuterium, a heavier form of hydrogen that ignites at lower temperatures, but this process is brief and limited. Brown dwarfs cool and dim over time, eventually becoming cold, dark objects drifting through space, invisible except in infrared surveys. They're surprisingly common, perhaps as numerous as stars, but their faintness makes them difficult to detect. Brown dwarfs represent the lower limit of stellar mass, the boundary below which gravity cannot compress matter enough to ignite the fusion that defines a star, objects that almost made it, forever trapped between planetary and stellar existence, glowing faintly in the darkness, reminders that not all clouds become suns. Stars form in clusters, before drifting apart. Most stars are born not alone but in groups, sometimes hundreds or thousands forming together in the same molecular cloud. These stellar clusters, bound by their mutual gravity, can remain intact for millions or even billions of years, but eventually most clusters dissolve, their stars drifting apart and dispersing throughout the galaxy. Open clusters, like the Pleiades, are relatively young and loosely bound, containing dozens to thousands of stars, while globular clusters are ancient and tightly packed, containing hundreds of thousands of stars in a spherical swarm. Our Sun likely formed in a cluster 4.5 billion years ago, but its siblings have long since scattered, now indistinguishable from other stars in the galaxy. Studying clusters allows astronomers to examine stars of the same age and composition, isolating the effects of mass on stellar evolution. When you see a cluster in the night sky, you're seeing a family of stars, born together, still travelling together, though eventually even these bonds will weaken, and each star will go its own way, alone in the vastness. The colour of a star reveals its temperature. The light from stars isn't white, but contains a spectrum of colours, and the dominant colour reveals the star's surface temperature. Hot stars emit more blue light, cool stars more red, following a principle called black body radiation. Astronomers use filters to measure the brightness in different colours, and the ratios between these measurements give precise temperature estimates. The hottest stars, blue-white giants, have surface temperatures exceeding 30,000 degrees Kelvin, while the coolest red dwarfs are below 4,000 degrees. Our Sun, at about 5,700 degrees, appears yellow-white. These colours are subtle to the human eye, which adapts to perceive most stars as white, but long exposure photographs reveal the true hues, blues and oranges and reds scattered across the sky. The colour also tells you about the star's age and mass, since these properties are linked to temperature. Looking up at the night sky, you're seeing a temperature map of distant suns, each colour a clue to the physics happening hundreds or thousands of light years away, information encoded in light that travelled across the void to reach your eyes tonight. Stars rotate, some rapidly, some slowly. Stars aren't stationary spheres but spinning objects, rotating around their axes just as Earth does. The rotation rate varies enormously. Some stars complete a rotation in hours, while others take months. Young stars tend to rotate faster, having conserved angular momentum from the collapsing cloud that formed them. As stars age, they lose angular momentum through stellar winds and magnetic braking, gradually slowing down. Our Sun rotates once every 25 days at its equator, slower at higher latitudes, since it's not a solid body but a ball of gas. Rapidly rotating stars are distorted by centrifugal force, becoming oblate, wider at the equator than at the poles. Some neutron stars rotate hundreds of times per second, their incredible density allowing such rapid spins without tearing apart. Rotation affects a star's magnetic field, its stellar wind, and even its evolution, making it more than just a curious detail, but a fundamental property that shapes the star's behaviour and appearance, adding motion to what seems from Earth like a static point of light. Stellar magnetic fields shape activity and flares. Many stars generate magnetic fields through the movement of charged particles in their interiors, a process called a dynamo. These fields can be weak or incredibly strong, and they shape the star's outer atmosphere, creating phenomena like sunspots, flares, and coronal mass ejections. Our Sun's magnetic field follows an 11-year cycle, waxing and waning in strength, causing variations in solar activity that affect Earth's space weather. More active stars can have flares thousands of times more powerful than the Sun's, releasing enormous bursts of radiation and particles. Magnetic fields can also channel stellar winds, creating complex structures in the space around the star. In some binary systems, magnetic fields from both stars interact, creating even more dramatic effects. The study of stellar magnetism is relatively young, but it's revealing that stars are not just glowing spheres, but dynamic, magnetically active objects, their fields reaching far beyond their visible surfaces, influencing the space around them, shaping the environment where planets orbit, connecting the star to its surroundings through invisible lines of force that twist and writhe and occasionally explode with sudden violence. Spectroscopy reveals what stars are made of. When starlight passes through a prism or diffraction grating, it spreads into a spectrum, a rainbow of colours crossed by dark lines. These lines, called absorption lines, occur at specific wavelengths where elements in the star's atmosphere absorb light. Each element produces a unique pattern of lines, a fingerprint that reveals its presence. By analysing these spectra, astronomers can determine not just what elements are present, but in what quantities, how fast the star is moving toward or away from us, whether it's rotating, and even whether it has a companion star. Spectroscopy revolutionised astronomy in the 19th century, transforming it from a science of positions to a science of physical understanding. Every star's spectrum tells a story about its composition, temperature, pressure, motion, and more. The technique works because of quantum mechanics. Each element's electrons can only absorb light at specific energies, creating those characteristic patterns. Looking at a star's spectrum is like reading its biography, learning what it's made of, where it came from, and where it's going, all from light that travelled across space to be dispersed into colours here on Earth. If your mind is starting to wander, that's perfectly fine. These theories aren't meant to be memorised, only experienced, like watching clouds drift across the sky. Protostars are stars in the process of forming. Before a star reaches the main sequence and begins steadily fusing hydrogen, it goes through a protostar phase, a period of contraction and heating that can last hundreds of thousands of years. A protostar is surrounded by a disk of gas and dust, material still falling inward, and it glows from the heat of gravitational contraction rather than fusion. As the protostar grows more massive and its core temperature rises, it becomes brighter and hotter, moving toward the conditions needed for fusion to begin. During this phase, the protostar may produce powerful jets of material from its poles, shooting outward at high speeds, clearing away surrounding gas and announcing the star's presence. When fusion finally ignites, the star settles onto the main sequence, and the protostar phase ends. Observing protostars is difficult because they're embedded in dense clouds that block visible light, but infrared telescopes can peer through the dust, revealing these stellar embryos, stars in the process of becoming, not yet shining with fusion's light but glowing with the promise of what they will be. T-Tauri stars are young and energetic. Young stars recently arrived on the main sequence or still approaching it, often display erratic behaviour, varying in brightness, producing strong stellar winds and erupting with flares. These are called T-Tauri stars, named after the first example discovered. They're typically less than 10 million years old, still surrounded by remnants of the disk from which they formed, and they haven't yet settled into the stable equilibrium that characterises mature stars. Tauri stars are common in star-forming regions, and studying them helps astronomers understand the transition from protostar to main sequence star. Their variability comes from several sources: magnetic activity, material still falling onto the star, and instabilities in the stellar structure as it adjusts to fusion. Planets are likely forming in the disks around these stars, condensing from the same material that built the star itself. T-Tauri stars represent stellar adolescence, the awkward phase between birth and maturity, energetic and unpredictable, still figuring out how to be a star, their light flickering and flaring as they settle into the long stability that will define most of their existence. Stellar parallax measures distances to nearby stars. The distance to stars was a mystery for millennia, but in the 19th century, astronomers finally measured it using parallax, the apparent shift in a star's position as Earth orbits the Sun. By observing a star 6 months apart, when Earth is on opposite sides of its orbit, astronomers could measure the tiny angle of shift and use geometry to calculate the distance. The nearest stars show parallaxes of about 1 arc-second, the width of a coin seen from several kilometres away, while more distant stars show smaller shifts, eventually becoming too small to measure from Earth's surface. Space telescopes like Gaia have measured parallaxes for billions of stars with incredible precision, creating a three-dimensional map of our galactic neighbourhood. Parallax only works for relatively nearby stars, a few thousand light-years at most, but it provides the foundation for the cosmic distance ladder, the series of techniques that allow astronomers to measure distances across the universe. Every distance measurement in astronomy ultimately traces back to parallax, to the simple geometry of Earth's orbit, making this ancient technique the foundation of our understanding of cosmic scale. Red dwarfs are the most common stars. Small, cool stars called red dwarfs make up about 70% of all stars in the galaxy, yet not a single one is visible to the naked eye. They're simply too dim, despite being the most numerous, their faint glow requiring telescopes to detect. Red dwarfs have masses between about 8 and 50% of the Sun's mass, and they burn their hydrogen so slowly that their lifetimes exceed the current age of the universe. The oldest red dwarfs, formed shortly after the Big Bang, are still on the main sequence, still steadily fusing hydrogen, and will continue for trillions of years more. This longevity makes them interesting for the search for life. Planets orbiting red dwarfs could remain habitable for far longer than planets around sun-like stars. However, red dwarfs are also prone to powerful flares, which could strip atmospheres from close-in planets. Despite their abundance, red dwarfs remained largely unknown until the 20th century, hidden by their dimness, a reminder that the most common things are sometimes the hardest to see, and that the galaxy is full of stars we cannot perceive without help, shining faintly in the darkness. The Sun is an average star. Our Sun, the source of Earth's light and warmth, the centre of our solar system, is in most ways utterly typical. It's a G-type main sequence star, yellow-white in colour, about halfway through its 10 billion year lifespan, with a mass and brightness right in the middle of the stellar range. There are many stars hotter and brighter and many cooler and dimmer, and the Sun falls comfortably in between. This averageness is actually reassuring. It suggests that Sun-like stars are common, and if our star could host life, perhaps many others can too. The Sun's stability, its steady output over billions of years, has allowed life on Earth to evolve and flourish. More massive stars would have shorter lifetimes, perhaps too short for complex life to develop. Less massive stars might have other complications. The Sun's ordinariness makes it special in a different way. It's a proof of concept, demonstrating that a star of this type can sustain a living world. Looking up at the night sky, many of those points of light are similar to our Sun, yellow stars of moderate temperature and mass, perhaps with their own planets, their own possibilities, ordinary suns like ours, shining quietly in the vastness. Supergiants are the largest stars. At the extreme end of stellar size are the supergiants, stars so enormous they would engulf multiple planets if placed in our solar system. Red supergiants like Betelgeuse and Antares have radii hundreds of times larger than the Sun, while hypergiants like UY Scuti may exceed 1,000 solar radii. If UY Scuti replaced our Sun, its surface would extend beyond Jupiter's orbit. These giants are rare, massive stars in the late stages of their lives, having exhausted their core hydrogen and swollen dramatically. Their surfaces are cool, giving them a red colour, but their total luminosity is immense, hundreds of thousands of times brighter than the Sun. Supergiants are unstable, pulsating and shedding mass through powerful stellar winds, losing substantial portions of their mass before they finally explode as supernovae. They represent the extreme of what a star can become. Size pushed to limits where the star barely holds together, gravity and radiation pressure in precarious balance. Looking at a supergiant, you're seeing a star in its final phase, burning through the last of its fuel, soon to die in spectacular fashion. Stellar nurseries are visible as nebulae. The regions where stars form, vast molecular clouds, are sometimes visible as nebulae, glowing clouds of gas and dust illuminated by the young stars within them or by nearby stars. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is one such stellar nursery about 1,300 light-years away, where hundreds of stars are currently forming. The nebula glows because ultraviolet light from hot young stars ionizes the surrounding hydrogen, causing it to emit visible light. Other nebulae are dark, visible only as silhouettes against brighter backgrounds, regions so dense with dust that they block light from stars behind them. These dark nebulae are often the sites of active star formation, though the stars themselves remain hidden until they emerge from their dusty cocoons. Nebulae come in many forms: emission nebulae, reflection nebulae, planetary nebulae, each with different causes and appearances, but all revealing the material between stars, the gas and dust from which stars form and to which they return, the raw material of stellar cycles visible as glowing clouds in the darkness, beautiful and generative. Stars can capture planets from other systems. While most planets form in the disk around their parent star, some planets might be captured, gravitationally stolen from another star during a close encounter, or adopted as free-floating planets drifting through space. In dense stellar environments like clusters, such interactions are more common, and simulations suggest that a significant fraction of planets might have been captured rather than formed in situ. A captured planet would likely have an unusual orbit, highly elliptical or inclined relative to other planets in the system. It's even possible that some objects in our outer solar system were captured from another star during the Sun's youth, when it was still in its birth cluster. The idea challenges the notion that planetary systems are isolated and unchanging, revealing them as dynamic, capable of exchanging material and objects with neighbouring systems. Captured planets would carry with them clues about their original system, chemical signatures that don't match their current star, making them valuable for understanding the early solar system and the processes that shape planetary systems over time. Stories of migration and adoption written in orbital dynamics. Stars lose mass as they age. Throughout their lives, stars gradually lose mass through stellar winds, radiation pressure, and in the case of massive stars, dramatic eruptions. This mass loss accelerates as stars age, particularly when they become red giants or supergiants, shedding substantial portions of their outer layers. For Sun-like stars, this mass loss is relatively gentle, the outer envelope gradually drifting away, eventually forming a planetary nebula. For massive stars, mass loss can be violent, with stellar winds carrying away several solar masses over a few million years. This mass loss affects the star's evolution, changing its structure, its temperature, and its ultimate fate. A star that begins with 50 solar masses might lose half its mass before exploding as a supernova, altering the type of remnant it leaves behind. The lost material enriches the interstellar medium, providing raw material for future generations of stars and planets. Mass loss connects a star to its surroundings, ensuring that even during life, not just at death, stars contribute to the cosmic cycle of matter, constantly exhaling into space, slowly diminishing but spreading their substance across the galaxy. The Chandrasekhar limit determines stellar remnants. There's a maximum mass for white dwarfs, about 1.4 times the mass of the Sun, called the Chandrasekhar limit. If a white dwarf exceeds this mass, electron degeneracy pressure can no longer support it against gravity, and it collapses further, either triggering a supernova or forming a neutron star. This limit explains why white dwarfs in binary systems can explode as Type Ia supernova when they accrete too much mass from a companion. Similarly, there's a maximum mass for neutron stars, about 2 to 3 solar masses, above which they collapse into black holes. These limits arise from the physics of degenerate matter, where particles are packed so tightly that quantum effects become important. The Chandrasekhar limit was calculated in the early 20th century by a young physicist on a ship to England, a prediction later confirmed by observations. These mass limits divide stellar remnants into distinct categories: white dwarfs, neutron stars, and black holes, each representing a different outcome of stellar death, determined not by the star's wishes but by the inexorable laws of physics, boundaries beyond which matter cannot resist gravity's pull. Stars can merge in binary systems. In close binary systems, where 2 stars orbit near each other, the stars can eventually spiral together and merge, creating a single, more massive star. This process, driven by the loss of orbital energy through tidal interactions or gravitational wave radiation, can take millions or billions of years. When the stars finally merge, the result depends on their masses and evolutionary states. 2 white dwarfs merging might explode as a supernova or form an unusual massive white dwarf. 2 neutron stars merging create a black hole and produce gravitational waves, and a burst of gamma rays, events recently detected by observatories on Earth. Stellar mergers can also create blue stragglers, stars that appear younger and bluer than they should be for their cluster's age, having been rejuvenated by the merger. These events are rare but important, contributing to the diversity of stellar populations and producing some of the most energetic phenomena in the universe. A merger is both an ending and a beginning. Two stars ceasing to exist as individuals but creating something new. A reminder that even in the cosmos, identities can blur and combine, creating outcomes impossible for either star alone. Stellar populations reveal galactic history. Astronomers divide stars into populations based on their age and composition. Population I stars, like our Sun, are relatively young, formed within the last few billion years, and contain significant amounts of heavy elements, metals in astronomical terms. Population II stars are older, formed when the galaxy was young, and contain fewer heavy elements, since the universe hadn't yet produced much beyond hydrogen and helium. Population III. Stars, purely theoretical so far, would be the very first stars, formed from primordial gas with no heavy elements at all. These populations trace the galaxy's chemical evolution, each generation of stars enriching the interstellar medium with heavier elements, making the next generation more metal-rich. Population II stars are found in globular clusters and the galactic halo, while Population I stars dominate the disk. Studying these populations reveals how the galaxy formed and evolved, how star formation has changed over time, and how the elements necessary for planets and life gradually accumulated. Each star carries in its composition a record of the galaxy's history, a chemical signature that tells when and where it was born, connecting individual stars to the larger story of cosmic evolution. If your eyes are growing heavy, don't fight it. Sleep is welcome here. The theories will continue whether you hear them or not, a quiet voice in the darkness. Stars emit neutrinos from their cores. Deep in a star's core, fusion reactions produce not just energy and light, but also neutrinos, nearly massless particles that barely interact with matter. Neutrinos stream out from the core at nearly the speed of light, passing through the star's outer layers without being absorbed or scattered, carrying away energy and information about the core's conditions. Detecting these neutrinos on Earth is incredibly difficult, requiring vast detectors buried deep underground to shield against other particles. But when astronomers do detect stellar neutrinos, they're seeing directly into the star's core, something impossible with light, which takes thousands of years to diffuse from core to surface. The Sun produces about 200 trillion neutrinos every second, and billions pass through your body every second, completely unnoticed. Neutrino astronomy is a new field, offering a unique window into stellar processes, revealing details about fusion rates, core temperatures, and even detecting supernovae before the light reaches us, since neutrinos escape immediately while light takes hours to fight through the collapsing star, making these ghostly particles messengers from the heart of stellar fires. Circumstellar disks are sites of planet formation. Around many young stars, astronomers observe disks of gas and dust, remnants of the cloud from which the star formed. These circumstellar disks are the birthplaces of planets, material gradually clumping together through collisions and gravitational attraction, growing from dust grains to pebbles, to boulders, to planetesimals, to planets. The process takes millions of years, and most of the disk's mass either falls onto the star, is blown away by stellar winds, or is incorporated into planets and smaller bodies. Observations of these disks reveal gaps and rings, likely carved by forming planets, providing direct evidence of planetary systems under construction. Some disks are massive enough to form multiple gas giant planets, while others might only produce rocky planets or remain planetless. Our solar system formed from such a disk 4.5 billion years ago, and studying other disks helps astronomers understand how common planets are and what factors determine the architecture of planetary systems. Each disk is a laboratory of planet formation, revealing the processes that transform diffuse gas into solid worlds, the alchemy that turns clouds into planets, operating around countless young stars throughout the galaxy. Stellar oscillations reveal internal structure. Stars aren't perfectly smooth and static, but oscillate, their surfaces moving in and out in complex patterns driven by waves propagating through their interiors. By measuring these oscillations, astronomers can probe the star's internal structure, much like seismologists study Earth's interior through earthquake waves. This field, called astroseismology, has revealed details about stellar cores, rotation rates at different depths, and the size and age of stars with unprecedented precision. The oscillations are tiny, surface motions of just meters, but they create measurable changes in the star's brightness and spectrum. Different oscillation modes penetrate to different depths, and by analysing the full spectrum of modes, astronomers can create a detailed picture of the star's interior, regions forever hidden from direct view. Our Sun oscillates with a period of about 5 minutes, its surface rising and falling in a complex pattern of millions of modes. Astroseismology has transformed our understanding of stellar structure, turning stars from opaque spheres into transparent objects whose interiors can be mapped, revealing the hidden machinery that powers their light, the layers and currents and flows that lie beneath the visible surface. Stars can have planets, inhabitable zones. Around every star, there's a region where temperatures are right for liquid water to exist on a planet's surface, neither too hot nor too cold, a zone called the habitable zone or Goldilocks zone. The location and width of this zone depend on the star's temperature and brightness. Around hot, bright stars, the habitable zone is far out, while around cool, dim stars it's close in. Earth orbits within the Sun's habitable zone, and astronomers have discovered thousands of exoplanets, many of which orbit within their stars' habitable zones, raising the possibility of life elsewhere. However, being in the habitable zone doesn't guarantee habitability. Planets also need the right atmosphere, magnetic field, and geological activity. Some planets in habitable zones might be too massive, crushing any surface life, while others might lack water entirely. Still, the habitable zone is a useful concept, a starting point for identifying worlds where life might exist. Looking up at the stars, some of those points of light have planets in their habitable zones, worlds where water might flow and life might have emerged, making the night sky not just a collection of suns but a map of potential homes, places where the universe might have experimented with biology, as it did here on Earth. Stellar metallicity affects planet formation. The abundance of heavy elements in a star, its metallicity, influences whether it has planets and what kinds. Stars with higher metallicity, more heavy elements, are more likely to have planets, especially gas giants, because the protoplanetary disk contains more solid material to form planetary cores. Our Sun has relatively high metallicity, about 1.5% heavy elements by mass, and it hosts a diverse planetary system. Stars with low metallicity, common in the galactic halo, rarely have planets, or only small rocky ones. This correlation suggests that the formation of gas giants requires a minimum amount of heavy elements to build cores massive enough to capture hydrogen and helium. Metallicity also affects the types of planets that form. High metallicity systems might produce more super-Earths, while low metallicity systems might only form small rocky worlds. This connection between stellar composition and planetary systems reveals that planet formation is sensitive to initial conditions, that the raw materials available in the protoplanetary disk shape the final architecture of the system, making some stars more likely to host diverse planetary families than others, a cosmic lottery determined by chemistry. The Eddington limit constrains stellar luminosity. There's a maximum luminosity a star can have for a given mass, called the Eddington limit, beyond which radiation pressure would blow the star apart. This limit arises because photons carry momentum, and when a star's radiation pressure exceeds the inward pull of gravity, the outer layers are pushed away. The Eddington limit depends on the star's mass and composition, and it's particularly important for massive stars which approach this limit during their lives. Some stars, called luminous blue variables, may briefly exceed the Eddington limit, shedding mass in violent eruptions. The limit explains why there's a maximum mass for stars, around 150 to 300 solar masses, above which the star would be unstable and quickly lose mass. It also plays a role in accretion onto compact objects like neutron stars and black holes, limiting how fast they can grow. The Eddington limit is a balance point, where radiation and gravity fight to a draw, and it defines the upper boundary of stellar luminosity, ensuring that stars, no matter how massive, cannot shine without limit, that there are rules even for giants. Constraints written into the physics of light and matter. Stars can explode as novae in binary systems. In binary systems where a white dwarf accretes material from a companion star, the accumulated hydrogen on the white dwarf's surface can ignite in a sudden thermonuclear explosion called a nova. This explosion doesn't destroy the white dwarf but blows off the accreted material, and the process can repeat, making some systems recurrent novae. Novae are much less energetic than supernovae, increasing in brightness by thousands of times rather than billions, but they're still dramatic events, visible across interstellar distances. The explosion occurs because the accreted hydrogen is compressed and heated by the white dwarf's gravity until it reaches fusion temperatures, but unlike in a normal star, the conditions are degenerate, and the fusion runs away, exploding rather than stabilizing. After the nova, the white dwarf settles down, and if accretion continues, the cycle repeats. Novae are relatively common. Several occur in our galaxy each year, and they contribute to the galactic chemical enrichment, though less significantly than supernovae. They're reminders that even dead stars can flare back to life, briefly, violently, in a last gasp of fusion before returning to darkness, waiting for the next accumulation of fuel. Stellar aberration reveals Earth's motion. As Earth orbits the Sun, the apparent positions of stars shift slightly, not due to parallax, but due to the finite speed of light combined with Earth's motion, an effect called stellar aberration. It's similar to how rain appears to come at an angle when you're moving, even if it's falling straight down. Stellar aberration causes stars to trace small ellipses in the sky over the course of a year, with the size of the ellipse depending on the star's position relative to Earth's orbital plane. This effect was first observed in the 18th century, and provided some of the earliest direct evidence that Earth orbits the Sun. Aberration is distinct from parallax, which depends on distance, while aberration is the same for all stars regardless of distance, depending only on Earth's velocity and the speed of light. Measuring aberration precisely requires careful observations over time, but it's now a routine correction in astrometry. The effect reveals the interplay between motion and light, showing that even the fixed stars aren't quite fixed, their positions shifting subtly as we move through space, a cosmic dance where our motion changes what we see, making the sky a reflection of our journey as well as a map of distant suns. Stars formed earlier were different. The first stars, forming a few 100 million years after the Big Bang, were very different from stars today. They formed from gas that contained only hydrogen and helium, no heavy elements, making them population 3 stars, a class never yet observed but predicted by theory. Without heavy elements, which help gas clouds cool and fragment, these first stars were likely very massive, perhaps hundreds of times the Sun's mass, and very hot, burning through their fuel in just a few million years before exploding as supernovae. These explosions seeded the universe with the first heavy elements, allowing the next generation of stars to be smaller and longer lived. Population 3 stars would have been extremely bright, and astronomers hoped to detect them with powerful telescopes by looking at the most distant and thus earliest regions of the universe. If found, they would reveal the transition from a universe of pure hydrogen and helium to one enriched with the elements necessary for planets and life. the first chapter in the story of cosmic chemical evolution, the moment when stars began the long process of creating the periodic table from primordial simplicity. If some theories feel confusing, that's okay. They're meant to be felt more than understood. Like music you don't need to analyze to enjoy. Magnetic fields can halt. Stellar collapse. In the densest regions of molecular clouds, where stars form, magnetic fields can provide support against gravitational collapse, slowing or even preventing star formation. The field lines thread through the gas, and as the gas tries to collapse, it must drag the magnetic field with it, which resists the motion. This magnetic support is most effective in low-density regions, and as the cloud becomes denser, gravity eventually overcomes the magnetic pressure, allowing collapse to proceed. However, the magnetic field doesn't disappear. It's carried inward with the infalling gas, becoming stronger as it's compressed, and it can affect the final properties of the forming star, influencing its rotation rate and the formation of jets. Understanding the role of magnetic fields in star formation is an active area of research, as they add complexity to the process, making it not just a matter of gravity and gas pressure, but also of magnetic forces and how they interact with the collapsing material. Magnetic fields are invisible threads woven through the galaxy, shaping the birth of stars, adding structure and resistance to the otherwise straightforward pull of gravity, making star formation a more intricate dance than it first appears. Stars can be ejected from galaxies. In rare cases, a star can be accelerated to such high speeds that it escapes the galaxy entirely, becoming an intergalactic traveller. These hypervelocity stars are thought to be accelerated by close encounters with supermassive black holes at galactic centres, where a binary star system is disrupted, one star captured by the black hole and the other flung outward at speeds exceeding the galaxy's escape velocity. Several hypervelocity stars have been discovered, moving at over 1 million kilometers per hour, fast enough to leave the Milky Way in tens of millions of years. Other mechanisms can also produce high-velocity stars, including supernova explosions in binary systems or interactions in dense star clusters. These stars are rare, but their existence shows that galaxies are not closed systems, that stars can be lost to intergalactic space, wandering forever in the void between galaxies, far from any stellar neighbours, alone in the darkness. It's a lonely fate to be ejected from your home galaxy, but also a kind of freedom, travelling where no star has travelled before, carrying light into regions where stars are rare, a solitary beacon in the vast emptiness between island universes. Stellar rotation affects surface features. Rapidly rotating stars can develop surface features like spots and bands, similar to sunspots and Jupiter's cloud bands. The rotation distorts the star's shape, making it oblate, and it affects the circulation patterns in the star's outer layers, creating regions of varying temperature and magnetic field strength. These features can be detected through variations in the star's brightness as it rotates, with spots causing dips in brightness when they face Earth. Some stars show very large spots, covering significant fractions of their surfaces much larger than sunspots. Rotation also affects the star's spectrum, broadening spectral lines due to the Doppler shift from the rotating surface, one side moving toward us and the other away. Studying these effects reveals details about stellar rotation, magnetic activity, and atmospheric dynamics, showing that stars are not featureless spheres, but complex dynamic objects with weather and activity patterns. The faster a star rotates, the more pronounced these effects become, making rapid rotators particularly interesting for studying stellar surfaces, revealing that stars have geography, in a sense, regions that differ from each other, patterns that change over time, making each star a unique world unto itself. The initial mass function describes star formation. When a cloud of gas collapses to form stars, it produces a distribution of masses, with many low-mass stars and few high-mass stars. This distribution, called the initial mass function, is remarkably similar in different star-forming regions, suggesting it's a fundamental property of star formation rather than depending on local conditions. The IMF shows that for every star like the Sun, there are about 10 red dwarfs and only a fraction of a star more massive than the Sun. This distribution has profound implications for galactic evolution, since low-mass stars live much longer and contribute less to chemical enrichment, while high-mass stars die quickly and produce most heavy elements. The shape of the IMF is still debated, particularly at the highest and lowest masses, but its general form is well established. Understanding why the IMF has this particular shape is a major question in astrophysics, related to how gas clouds fragment and how protostars compete for material. The IMF determines the overall properties of stellar populations, the ratio of bright to dim stars, the rate of supernovae, and the long-term fate of galaxies, making it a key parameter in models of cosmic evolution. Stars can have stellar companions of different types. Binary systems aren't always two similar stars. Often they consist of stars at different evolutionary stages or even different types of objects. A main sequence star might orbit a white dwarf, or a giant star might have a neutron star companion. These mixed pairs can lead to interesting interactions, such as mass transfer, where the larger star sheds material onto the compact companion, or tidal effects that alter the star's rotation and orbit. Some binaries are so close that they share a common envelope, their outer layers merging while their cores remain distinct. Other binaries are wide, the stars separated by thousands of astronomical units, barely interacting at all. The diversity of binary systems reflects the many ways stars can form and evolve together, and studying these systems reveals the full range of stellar behavior, from gentle coexistence to violent interaction. Each binary has its own story, its own dynamics, shaped by the masses, ages, and separation of its components, making binaries not just doubled stars but laboratories for studying stellar physics, where interactions and exchanges reveal processes invisible in solitary stars. Stellar winds interact with interstellar medium. As stellar winds stream outward from stars, they collide with the surrounding interstellar medium, creating shock waves and bubbles. The Sun's solar wind creates a bubble called the heliosphere, extending far beyond Pluto, where it meets the interstellar medium in a region called the heliopause. Massive stars with powerful winds create much larger bubbles, sometimes tens or hundreds of light years across, sweeping up and compressing the surrounding gas. These bubbles can trigger star formation in the compressed gas at their edges, creating new generations of stars, a process called triggered star formation. The interaction between stellar winds and the interstellar medium also heats and ionizes the gas, contributing to the diffuse glow seen in regions of active star formation. When multiple massive stars form in the same region, their combined winds create superbubbles, enormous cavities in the interstellar medium that can persist for millions of years. These structures shape the galaxy's appearance and evolution, redistributing gas, triggering new star formation, and enriching the interstellar medium with heavy elements, connecting individual stars to the larger galactic ecosystem, making stellar winds not just an outflow but a creative force. Stars can form from recycled material. The gas from which stars form isn't pristine but has been processed through previous generations of stars. Each generation enriches the gas with heavy elements, increasing the metallicity and changing the properties of subsequent star formation. The Sun formed from gas that had already been through at least one or two cycles of star formation and death, which is why it contains elements like carbon, oxygen, and iron. This recycling means that stars are connected across time, each generation building on the ashes of the last, a cosmic relay where matter is passed from star to star, transformed and enriched with each cycle. The process has been ongoing for over 10 billion years in our galaxy, and it will continue for billions more, until eventually the gas is exhausted and star formation ceases. But for now, the cycle continues, old stars dying and new stars forming, each carrying within it the legacy of all the stars that came before, a lineage written in chemical composition, connecting the first stars to the latest, making stellar evolution not just the story of individual stars, but a collective narrative spanning the galaxy's history. The Hertzsprung gap represents rapid evolution. On the Hertzsprung-Russell diagram, there's a region between the main sequence and the giant branch where very few stars are found, called the Hertzsprung gap. This gap exists because stars pass through this region very quickly, in just a few million years, as they transition from core hydrogen burning to shell hydrogen burning. During this phase, the star's structure is adjusting rapidly, and its position on the diagram changes quickly, making it unlikely to observe a star in this state. The gap is more pronounced for certain mass ranges, and less so for others, depending on the details of stellar evolution. Finding stars in the Hertzsprung gap is valuable because they are in a brief transitional phase, and studying them reveals how stars make the leap from main sequence to giant, a critical stage in their evolution. The gap is a reminder that stars spend most of their time in stable phases and relatively little time in transitions, making the transitions harder to observe but no less important. Brief moments of rapid change between long periods of stability, the stellar equivalent of punctuated equilibrium, where evolution happens in bursts rather than gradually. Stars can have planetary nebulae. When a sun-like star exhausts its fuel and sheds its outer layers, the expelled gas forms a planetary nebula, a glowing shell expanding around the hot white dwarf core. Despite the name, planetary nebulae have nothing to do with planets. They were named centuries ago because their round shapes resemble planets through small telescopes. These nebulae are beautiful, often showing intricate structures, rings, bubbles, and jets, shaped by the star's rotation, magnetic fields, and interactions with any companion stars. The nebula glows because ultraviolet light from the hot central star ionizes the gas, causing it to emit visible light in characteristic colors: red from hydrogen, green from oxygen, blue from nitrogen. Planetary nebulae last only a few tens of thousands of years before dispersing into the interstellar medium, a brief but beautiful finale to the star's life. They return to space the elements created in the star's interior, enriching the galaxy with carbon, nitrogen, and oxygen, elements essential for life. Each planetary nebula is unique, a cosmic artwork shaped by the dying star's final breath, a monument that lasts a cosmic moment before fading, leaving only the white dwarf behind, cooling in the darkness. Stellar multiplicity is common. Many stars that appear single are actually multiple systems when examined closely. Surveys suggest that perhaps half of all sun-like stars have at least one companion, and the fraction is even higher for more massive stars. These companions can be other stars, brown dwarfs, or even massive planets, and they can orbit at various distances, from nearly touching to separated by thousands of astronomical units. The presence of companions affects stellar evolution, planetary system formation, and the star's ultimate fate. Close binaries can merge or transfer mass, while wide binaries evolve independently but may still influence each other's planetary systems through gravitational perturbations. Some stars are in triple or quadruple systems, with hierarchical structures where pairs orbit each other and then orbit a common center with other pairs. The prevalence of multiple systems suggests that star formation often produces groups rather than individuals, that the collapse of a gas cloud naturally fragments into multiple cores, making stellar companionship the rule rather than the exception, and solitary stars like the Sun perhaps somewhat unusual, alone in a universe where most stars have siblings, orbiting together through the galaxy's long night. There's no test at the end, no need to prove you are listening. Your mind can wander where it wants, to memories, to dreams, to nothing at all. Stars can produce. Gamma-ray bursts. The most energetic explosions in the universe, gamma-ray bursts, are thought to be produced by certain types of stellar deaths. Long-duration gamma-ray bursts, lasting more than 2 seconds, are associated with the collapse of massive stars into black holes, accompanied by jets of material shooting out at nearly the speed of light. These jets, if pointed toward Earth, produce a brief but intense burst of gamma rays, followed by an afterglow at longer wavelengths. Short-duration gamma-ray bursts lasting less than 2 seconds are thought to come from neutron star mergers. In both cases, the energy released is staggering, equivalent to the Sun's entire lifetime output compressed into seconds. Gamma-ray bursts are rare, occurring perhaps once per day in the observable universe, and they're visible across cosmological distances, making them useful for studying the early universe. A gamma-ray burst in our galaxy, if pointed at Earth, could be catastrophic, but fortunately they're rare, and the odds of one occurring nearby and aimed at us are extremely small. These bursts represent the most violent stellar events, the ultimate endpoints of certain evolutionary paths, flashes of light that briefly outshine everything else. Stars can be studied through asteroids. Some asteroids, particularly those in the main belt, contain material that predates the formation of planets, preserving a record of the early solar system and the conditions in the protoplanetary disk. By studying these asteroids, scientists learn about the composition of the material from which the Sun and planets formed, including the isotopic signatures that reveal details about the molecular cloud and nearby supernovae that contributed to the solar system's formation. Meteorites, fragments of asteroids that fall to Earth, provide direct samples of this ancient material, allowing laboratory analysis with precision impossible for distant stars. Some meteorites contain pre-solar grains, tiny particles that formed around other stars before the solar system existed, carried into the protoplanetary disk and incorporated into asteroids. These grains are literally stardust, fragments of other stars, and studying them reveals the properties of those long-dead stars, their compositions, their nucleosynthesis processes, their deaths. In this way, asteroids and meteorites serve as archives of stellar history, connecting our solar system to the broader galactic story, carrying within them the legacy of stars that shone and died before the Sun was born, making every meteorite a messenger from the ancient cosmos. Stellar populations evolve over time. The mix of stars in a galaxy changes over time as old stars die and new stars form. Early in a galaxy's history, star formation is vigorous, producing many massive stars that quickly die as supernovae, enriching the gas with heavy elements. As the galaxy ages, the gas is gradually consumed, star formation slows, and the average stellar age increases. Elliptical galaxies, which have little gas left, contain mostly old red stars, while spiral galaxies, which still have gas, contain a mix of old and young stars. The colour of a galaxy reflects its stellar population. Blue galaxies have active star formation, while red galaxies are dominated by old stars. Over billions of years, galaxies can transition from blue to red as they exhaust their gas or lose it through interactions with other galaxies. This evolution means that the night sky is not static but changing, very slowly, as stars are born and die, as the chemical composition of the galaxy shifts, as the population of stars evolves from young and hot to old and cool, making the galaxy's appearance a snapshot of a much longer story, a moment in a billion-year transformation. Stars can have unusual compositions. While most stars have broadly similar compositions, mostly hydrogen and helium with a few % heavy elements, some stars show unusual abundances of certain elements. Carbon stars have more carbon than oxygen in their atmospheres, making them appear red and producing complex carbon-based molecules. Barium stars have excess barium and other heavy elements, likely acquired from a companion star that has since become a white dwarf. Some stars show enhancements in elements like lithium, technetium, or rare earth elements, signatures of specific nucleosynthesis processes or mass transfer events. These unusual compositions provide clues about stellar evolution, nucleosynthesis, and binary interactions, revealing processes that aren't obvious in normal stars. Studying chemically peculiar stars helps astronomers refine models of how elements are created and distributed, how stars interact in binaries, and how material is exchanged between stars. Each unusual star is a puzzle, its composition a clue to its history. And solving these puzzles advances our understanding of stellar physics, showing that not all stars follow the same path, that there are variations and exceptions, making the stellar population diverse and complex, a tapestry of different histories and processes rather than a uniform collection of identical objects. Stellar flares can affect exoplanet habitability. Many stars, particularly young stars and red dwarfs, produce powerful flares, sudden releases of magnetic energy that emit intense radiation across the spectrum. These flares can be thousands of times more energetic than solar flares, and they occur much more frequently on some stars. For planets orbiting close to their stars, as is common in red dwarf systems where the habitable zone is near the star, these flares can strip away atmospheres, sterilize surfaces with ultraviolet and X-ray radiation, and make the environment hostile to life. However, some models suggest that planets with strong magnetic fields or thick atmospheres might be protected, and life might adapt to the flare environment. The impact of stellar flares on habitability is an active area of research, important for assessing which exoplanets might support life. Flares are a reminder that not all stars are as stable as the Sun, that stellar activity can vary widely, and that the habitability of a planet depends not just on its distance from its star, but also on the star's behavior, its magnetic activity, its flares and winds, making the search for life a matter of understanding stellar physics as much as planetary conditions. Stars can form in isolation. While most stars form in clusters, some form in relative isolation, either because they formed in a small cloud that produced only one or a few stars, or because they were ejected from their birth cluster early in their lives. These isolated stars, sometimes called field stars, make up a significant fraction of the stellar population, and they evolve without the gravitational influence of nearby stars, making their planetary systems potentially more stable. Our Sun is a field star now, though it likely formed in a cluster, its siblings long since dispersed across the galaxy. Isolated star formation is less efficient than cluster formation, requiring specific conditions, but it does occur, particularly in regions where the gas density is lower. Studying isolated stars helps astronomers understand the full range of star formation environments and how the initial conditions affect stellar and planetary evolution. Isolated stars are also less likely to experience close encounters with other stars, which can disrupt planetary orbits or strip away outer planets, making them perhaps more favourable for the long-term stability of planetary systems. Though this advantage comes with the loneliness of having no stellar neighbours, no companion suns to share the darkness. Stars can be used as cosmic clocks. The ages of stars can be estimated through various methods, and these ages provide constraints on the age of the universe and the history of galaxies. The oldest stars, found in globular clusters, are about 13 billion years old, just slightly younger than the universe itself, confirming that these clusters formed very early in cosmic history. By studying the properties of these ancient stars, their compositions, their luminosities, their positions on the Hertzsprung-Russell diagram, astronomers can refine models of stellar evolution and cosmology. Stars with well-determined ages also serve as calibration points for other age-dating methods, such as radioactive decay in meteorites or the expansion rate of the universe. In this way, stars are cosmic clocks ticking away the eons, their properties changing predictably with time, allowing astronomers to read their ages and, by extension, the ages of the structures they inhabit, connecting the lifetimes of individual stars to the age of the universe itself, making stellar evolution a tool for cosmology, a way to measure time on the grandest scales. Using the slow changes in stars to mark the passage of billions of years, stellar archaeology studies ancient stars. By analysing the compositions of the oldest stars, astronomers can learn about the early universe, the first generations of stars, and the processes that enrich the primordial gas with heavy elements. These ancient stars, with very low metallicities, formed from gas that had been enriched by only a few supernovae, and their compositions reflect the nucleosynthesis yields of those early explosions. Studying these stars reveals what the first stars were like, how they died, and how quickly the universe was chemically enriched. Some ancient stars show unusual abundance patterns, suggesting they were enriched by specific types of supernovae, or by the first stars, population 3 stars, which have never been directly observed. Stellar archaeology is like reconstructing history from fragmentary records, each ancient star a clue to the early universe, its composition a message from a time when the cosmos was young and the first stars were just beginning to light the darkness. These stars are survivors, having lived for over 10 billion years, witnesses to the galaxy's entire history, carrying in their atmospheres the chemical signatures of the universe's youth, making them invaluable for understanding cosmic origins. Stars can produce planetary systems with diverse architectures. The discovery of thousands of exoplanets has revealed that planetary systems come in an astonishing variety of configurations. Some systems have hot Jupiters, giant planets orbiting very close to their stars, while others have super-Earths, planets larger than Earth but smaller than Neptune in tight orbits. Some systems have planets in highly elliptical orbits, while others have planets in nearly circular orbits. Some systems have multiple planets in resonance, their orbital periods related by simple ratios, while others have planets scattered chaotically. This diversity suggests that planet formation and evolution are complex processes, sensitive to initial conditions, and capable of producing many different outcomes. Our solar system, with its small rocky planets close to the Sun and giant planets farther out, is just one possible configuration, perhaps not even the most common. Understanding this diversity requires studying many planetary systems, looking for patterns and correlations, and refining models of planet formation and migration. Each planetary system is a unique experiment in how planets form and evolve, shaped by the properties of the protoplanetary disk, the star's mass and activity, and the gravitational interactions among planets, making the study of exoplanets a window into the full range of planetary possibilities. Stars can be gravitationally lensed. When a massive object passes between a distant star and Earth, its gravity can bend the star's light, magnifying and distorting it, an effect called gravitational lensing. This phenomenon, predicted by Einstein's general relativity, has been observed many times, and it's used to study both the lensing object and the distant star. Gravitational microlensing, where a star in our galaxy lenses a more distant star, creates a temporary brightening that can last days or weeks, and it's used to detect planets around the lensing star since the planet's gravity creates a brief additional spike in brightness. Gravitational lensing also allows astronomers to study distant stars that would otherwise be too faint to observe, magnifying their light and revealing details about their properties. The effect is a beautiful confirmation of general relativity, showing that mass curves space-time and that light follows these curves, making gravity not just a force but a shaping of the very fabric of the universe. Lensing connects distant stars to nearer ones, using the gravity of one to reveal the light of another, a cosmic telescope created by the universe itself, allowing us to see farther and more clearly than we could otherwise. Stars can form in galactic collisions. When galaxies collide, their gas clouds collide too, compressing and triggering intense bursts of star formation. These starbursts can produce thousands or even millions of stars in a relatively short time, far more than the galaxy would produce normally. The newly formed stars are often massive and short-lived, leading to a surge of supernovae and heavy element production. Starburst galaxies are bright in infrared light, the heat from young stars absorbed by dust and re-emitted at longer wavelengths. The Milky Way has experienced several minor mergers in its history, each likely triggering episodes of enhanced star formation, and it's currently in the process of merging with smaller galaxies like the Sagittarius dwarf. In a few billion years, the Milky Way will collide with the Andromeda Galaxy, and this collision will trigger a major starburst, reshaping both galaxies and producing a new generation of stars. Galactic collisions are not violent in the sense of stars colliding. Stars are too far apart for that, but they're transformative, mixing gas, triggering star formation, and altering the structure and evolution of the galaxies involved, making collisions not destructive but creative, forging new stars from the chaos of merging galaxies. If you've drifted in and out, that's perfect. These theories are companions, keeping you company as you drift, asking nothing, demanding nothing, just offering gentle wonder. Stars can exhibit pulsations in multiple modes. Some variable stars pulsate in complex patterns, with multiple oscillation modes active simultaneously, creating intricate light curves. These multimode pulsators allow astroseismologists to probe stellar interiors with great detail, as each mode penetrates to a different depth and is sensitive to different layers. By analysing the frequencies and amplitudes of the various modes, astronomers can determine the star's mass, radius, age, internal rotation, and even the size of its core. The Sun is a multi-mode pulsator, with millions of oscillation modes, though most are very weak. More dramatic pulsators, like Delta Scuti stars or Beta Cephei stars, show larger amplitude variations and fewer modes, making them easier to study. The complexity of multi-mode pulsations reflects the complexity of stellar interiors, the layers and gradients and currents that exist beneath the surface, invisible to direct observation, but revealed through the subtle movements of the star's surface. Each mode is like a note in a chord, and together they create a symphony that tells the star's story, a music of spheres that astronomers can decode, translating oscillations into knowledge, vibrations into understanding, making pulsating stars not just variable but eloquent, speaking in frequencies about their hidden depths. Stars can have convective or radiative envelopes. The outer layers of stars transport energy from the interior to the surface through either convection, where hot gas rises and cool gas sinks, or radiation, where photons diffuse outward. Which mechanism dominates depends on the star's mass and evolutionary state. Sun-like stars have radiative cores and convective envelopes, while more massive stars have the opposite, convective cores and radiative envelopes. Red dwarfs are fully convective, with no radiative zone at all. These differences affect the star's magnetic field generation, its surface activity, and its mixing of material between layers. Convective envelopes create complex surface patterns, granulation and supergranulation, visible on the Sun's surface as a boiling texture. Radiative envelopes are smoother, with less surface activity. The transition between convective and radiative zones can create shear layers, where rotation rates change, generating magnetic fields through dynamo processes. Understanding energy transport in stars is crucial for modelling their structure and evolution, and it reveals that stars are not uniform but layered, with different regions behaving differently, each layer contributing to the star's overall behaviour, making stellar interiors complex and dynamic, regions of flow and radiation, currents and gradients hidden beneath the glowing surface. Stars can be chemically tagged to birth clusters. By measuring the detailed chemical composition of stars, astronomers can sometimes identify stars that formed in the same cluster, even if the cluster is long since dispersed. This technique, called chemical tagging, relies on the fact that stars born from the same gas cloud have nearly identical abundances of many elements, a chemical fingerprint unique to that cloud. By finding stars with matching fingerprints scattered across the galaxy, astronomers can reconstruct the original cluster membership and study how clusters dissolve and disperse over time. This technique has revealed that the Sun likely has siblings somewhere in the galaxy, stars born in the same cluster 4.5 billion years ago, now spread across thousands of light years. Finding these solar siblings is difficult, requiring precise measurements of dozens of elements. But it's possible, and it would provide insights into the Sun's birth environment and the early solar system. Chemical tagging connects stars across space and time, linking them through shared origins, making the galaxy not a collection of unrelated individuals but a family with lineages and relationships. Stars that are siblings or cousins, born from the same clouds, carrying the same chemical legacy, scattered by time but still connected through composition. Stars can produce dust in their atmospheres. Cool stars, particularly red giants and supergiants, can have temperatures low enough in their outer atmospheres for dust grains to condense, tiny particles of silicates, carbon, or other compounds. This dust absorbs and scatters starlight, affecting the star's observed brightness and colour, and it's eventually carried away by stellar winds, enriching the interstellar medium with solid particles. Dust production is an important step in the cosmic cycle of matter, as dust grains provide surfaces where molecules can form, including complex organic molecules, and they serve as the building blocks of planets. Some stars produce so much dust that they're almost invisible at optical wavelengths, appearing only in infrared light, where the dust's thermal emission dominates. These dust-enshrouded stars, often in late stages of evolution, are factories of cosmic dust producing the raw material for future planetary systems. The dust they create will eventually be incorporated into new stars and planets, continuing the cycle of matter through the universe, making dust not just debris but a crucial component of cosmic evolution. Tiny particles that carry elements from stars to space, from death to new birth, connecting stellar generations through grains smaller than the width of a hair. Stars can have planets that migrate. Planets don't necessarily stay in the orbits where they formed. Interactions with the protoplanetary disk, gravitational interactions with other planets, or tidal effects with the star can cause planets to migrate inward or outward, sometimes dramatically. Hot Jupiters, giant planets orbiting very close to their stars, likely formed farther out and migrated inward, losing angular momentum to the disk or to other planets. Some planets may migrate all the way to the star and be consumed, while others may be ejected from the system entirely, becoming rogue planets drifting through interstellar space. Migration can reshape planetary systems, causing planets to collide or be ejected, and it can deliver water and organic molecules to inner planets, potentially affecting habitability. Understanding planetary migration is crucial for interpreting the observed architectures of exoplanetary systems, explaining why some systems look very different from our solar system. Migration makes planetary systems dynamic, evolving over millions of years, not frozen in their initial configurations but constantly adjusting, planets moving, interacting, reshaping the system, making the final architecture the result of a long and complex history, a story of motion and change rather than static permanence. Stars can be disrupted by tidal forces. If a star passes too close to a supermassive black hole, the black hole's tidal forces can tear the star apart in an event called a tidal disruption event. The side of the star closer to the black hole feels stronger gravity than the far side, stretching the star until it's ripped apart. About half the star's material falls into the black hole, producing a bright flare of radiation as it heats up, while the rest is flung outward. These events are rare, occurring perhaps once every 10,000 years in a galaxy, but they're spectacular when they happen, briefly outshining the entire galaxy. Observing tidal disruption events allows astronomers to study supermassive black holes in otherwise quiet galaxies, where the black hole isn't actively accreting material. The flares can last months or years, gradually fading as the material is consumed or dispersed. Tidal disruption events are violent endings for stars, but they're also informative, revealing the presence and properties of black holes, demonstrating the extreme tidal forces near these objects, and showing that even stars, which seem permanent on human timescales, can be destroyed suddenly, torn apart by gravity, their material scattered or swallowed, a dramatic fate that awaits any star unlucky enough to wander too close to a black hole. Stars can form in triggered waves. Star formation can propagate through a region in waves, where the formation of one generation of stars triggers the formation of the next. Massive stars, with their powerful winds and eventual supernova, compress surrounding gas, creating dense regions where new stars can form. These new stars, once they mature, trigger the next generation and so on, creating a wave of star formation moving through the galaxy. This process, called sequential star formation, can explain the age gradients seen in some star-forming regions, where stars on one side are older than those on the other. It also contributes to the overall star formation rate in galaxies, as triggered star formation can sustain itself for millions of years, cycling through multiple generations. The waves move slowly, just a few light years per million years, but over time they can propagate across large sections of a galaxy. Triggered star formation connects stellar generations, making star formation not an isolated event but a collective process, where each generation influences the next, creating patterns and structures in the distribution of stars, waves of creation moving through the galaxy, driven by the deaths of massive stars and the compression of gas, a cascade of birth following death, endlessly repeating. Stars can be observed across cosmic time. Because light travels at a finite speed, looking at distant stars means looking back in time. Stars we see in distant galaxies appear as they were millions or billions of years ago, when their light began its journey to us. This allows astronomers to study stellar populations at different epochs of cosmic history, seeing how stars and galaxies have changed over time. The most distant stars we can see, in galaxies billions of light years away, appear as they were when the universe was young, less than 1 billion years old. These early stars were different from stars today, formed from less enriched gas. And studying them reveals the conditions in the early universe. By comparing stellar populations at different distances, and thus different times, astronomers can trace the evolution of galaxies, the build-up of heavy elements, and the changing rate of star formation over cosmic history. In this way, stars are not just objects in space, but also markers of time, each one a snapshot of a particular moment in the universe's history. And by looking at many stars at many distances, astronomers can reconstruct the story of how the universe has changed, how stars have evolved, how galaxies have grown, making astronomy a form of time travel, seeing the past written in the light of distant stars. We're near the end now. Let the final theories wash over you like gentle waves, carrying you deeper into rest, into calm, into the soft embrace of sleep. Stars can exhibit sympathetic flares in binaries. In close binary systems, flares on one star can trigger flares on its companion, a phenomenon called sympathetic flaring. This occurs because the stars are magnetically connected, their magnetic fields interacting across the space between them, and a flare on one star can send a disturbance through the shared magnetic structure, triggering a response on the other star. Sympathetic flares reveal the complexity of magnetic interactions in binary systems, showing that the stars don't evolve independently, but influence each other even without physical contact. Studying these interactions helps astronomers understand stellar magnetic fields and how they extend beyond the star's surface. Sympathetic flaring is most common in very close binaries, where the stars are only a few stellar radii apart and their magnetic fields are strongly intertwined. It's a reminder that binary stars are systems, not just pairs, with connections and interactions that shape both stars' behavior, making them more than the sum of their parts. Two stars acting in concert, their magnetic fields dancing together, flares echoing between them, a cosmic conversation conducted in bursts of energy and light, visible across light years, evidence of connection and influence spanning the void between stars. Stars can be used to test general relativity. The extreme conditions near certain stars, particularly neutron stars and white dwarfs, allow astronomers to test Einstein's theory of general relativity and strong gravitational fields. Observations of binary pulsars, where a neutron star orbits another neutron star or a white dwarf, have confirmed predictions of general relativity with incredible precision, including the emission of gravitational waves, which cause the orbit to gradually decay. The first indirect detection of gravitational waves came from observing the orbital decay of a binary pulsar, exactly matching the predictions of general relativity. More recently, gravitational wave detectors have directly observed the mergers of neutron stars and black holes, providing further confirmation. White dwarfs also serve as laboratories for testing relativity, their strong gravity causing measurable effects on light passing near them. These tests show that general relativity holds even in extreme conditions, validating Einstein's theory and ruling out alternative theories of gravity. Stars, in their most extreme forms, become tools for fundamental physics, their gravity so strong that space-time itself is noticeably curved, allowing astronomers to probe the nature of space, time, and gravity, using stars as natural laboratories that produce conditions impossible to recreate on Earth, making stellar astronomy not just about stars, but about the fundamental laws that govern the universe. Stars can have habitable zones that change over time. As stars evolve, their luminosity changes, and so does the location of the habitable zone, the region where liquid water can exist on a planet's surface. For a sun-like star, the habitable zone moves outward as the star ages and brightens, meaning that planets that are too cold now might become habitable in the future, while planets that are habitable now might become too hot. Earth, for example, is near the inner edge of the Sun's current habitable zone, and in about 1 billion years, as the Sun continues to brighten, Earth will likely become too hot for liquid water. However, Mars might become habitable as it moves into the habitable zone. For red dwarfs, which brighten very slowly, the habitable zone remains relatively stable over trillions of years, offering long-term habitability for any planets there. For massive stars, which evolve quickly, the habitable zone moves rapidly, and planets might only be habitable for a few million years before the star becomes too bright or dies. Understanding how habitable zones change over time is important for assessing the long-term prospects for life on exoplanets, recognizing that habitability is not permanent but depends on the star's evolutionary state, making the search for life a time-dependent question where the age of the star matters as much as the position of the planet. Stars can produce cosmic rays, high-energy particles called cosmic rays, mostly protons and atomic nuclei travelling at nearly the speed of light, originate from various sources, including supernova remnants, where particles are accelerated by shock waves in the expanding debris. These cosmic rays permeate the galaxy, constantly bombarding Earth and other planets, and they play a role in the chemistry of the interstellar medium, ionizing gas and affecting the formation of molecules. Cosmic rays from the Sun, produced by solar flares and coronal mass ejections, are less energetic but more numerous, and they can affect Earth's atmosphere and magnetic field. The most energetic cosmic rays, with energies far exceeding anything achievable in particle accelerators, likely come from more exotic sources, possibly supermassive black holes or gamma-ray bursts. Studying cosmic rays reveals the violent processes in the universe, the acceleration mechanisms that can boost particles to incredible energies, and the magnetic fields that guide them through space. Cosmic rays are messengers from distant stellar explosions, carrying information about conditions in the galaxy, and they connect stars to the space between them, filling the galaxy with high-energy particles, remnants of stellar deaths, travelling through the darkness, occasionally striking Earth, where they're detected by instruments and studied, revealing the energetic side of stellar evolution, the legacy of explosions that occurred long ago and far away. Stars can be found in stellar streams. When galaxies or star clusters are tidally disrupted by the gravity of a larger galaxy, their stars are stretched into long, thin streams that orbit the galaxy. These stellar streams, visible as overdensities of stars in the galaxy's halo, trace the orbits of the disrupted objects and provide information about the galaxy's gravitational potential and dark matter distribution. Several stellar streams have been discovered around the Milky Way, remnants of small galaxies and globular clusters that were torn apart by the Milky Way's gravity. The stars in these streams share common motions and compositions, marking them as members of the same original object. Studying stellar streams helps astronomers understand the history of galactic mergers and the structure of the galaxy's dark matter halo. The streams are faint and difficult to detect, requiring large surveys that map the positions and motions of millions of stars, but they're valuable clues to the galaxy's past, showing that the Milky Way has grown over time by consuming smaller galaxies, that the halo is full of debris from these ancient collisions, making the galaxy not a static structure, but the result of billions of years of growth and change, an accumulation of stars from many sources woven together by gravity into a single system. Stars can form in dense cluster cores. In the centres of dense star clusters, particularly globular clusters, stars are packed so closely that interactions and collisions are relatively common. These interactions can lead to exotic stellar objects, blue stragglers formed by collisions or mass transfer, X-ray binaries where a neutron star accretes from a companion, and even intermediate mass black holes formed by the merger of multiple stars. The dense environment also affects the formation and evolution of planetary systems, as close encounters can disrupt orbits or strip away outer planets. Studying cluster cores reveals the effects of high stellar density on stellar evolution, showing that stars in these environments evolve differently from isolated stars. The cores of globular clusters are like stellar laboratories, where the effects of gravity and stellar interactions are amplified, creating conditions found nowhere else in the galaxy. These regions are dynamic, with stars constantly moving, interacting and sometimes merging, creating a complex and ever-changing population. The cores are also bright, with many luminous stars packed into a small volume, making them visible even in distant galaxies, beacons of stellar density, regions where the rules of stellar evolution are modified by the sheer number of stars, making cluster cores unique environments different from the sparse field where most stars reside, places where stars live in crowded proximity, influencing each other's fates. Stars can have magnetic cycles. Many stars exhibit magnetic cycles similar to the Sun's 11-year solar cycle, where the magnetic field strength and configuration change over time, affecting the number and distribution of star spots and the level of stellar activity. These cycles are driven by the star's internal dynamo, the process that generates the magnetic field through the motion of conducting material in the star's interior. Some stars have cycles shorter than the Sun's, while others have longer cycles, and some show no clear cycle at all, their magnetic activity appearing chaotic. Studying stellar magnetic cycles helps astronomers understand the dynamo process and how it depends on the star's rotation rate, mass, and internal structure. Cycles also affect the star's output of ultraviolet and X-ray radiation, which can impact the atmospheres and habitability of any orbiting planets. Long-term monitoring programs track stellar activity over decades, building up records of magnetic cycles for many stars, revealing patterns and correlations that inform models of stellar magnetism. Magnetic cycles show that stars are not static but dynamic, their magnetic fields waxing and waning, their activity levels rising and falling, creating a rhythm that plays out over years or decades, a slow pulse that modulates the star's behavior, making stellar activity a time-variable phenomenon, not constant but cycling, adding another layer of complexity to stellar evolution. Stars can be observed in different wavelengths. Stars emit light across the electromagnetic spectrum, from gamma rays to radio waves, and observing them at different wavelengths reveals different aspects of their physics. Optical light shows the star's surface, while ultraviolet light reveals the hot chromosphere and corona. X-rays come from the hottest regions, such as flares and the coronae of active stars, while infrared light penetrates dust and shows cooler components like circumstellar disks. Radio observations can detect stellar winds and magnetic activity. By combining observations at multiple wavelengths, astronomers build a complete picture of the star, understanding its structure, activity, and environment. Multi-wavelength astronomy has revealed that stars are more complex than they appear in visible light, with layers and structures that emit at different wavelengths, each wavelength providing unique information. Some stars are bright in X-rays but faint in optical light, while others are the reverse. The full spectrum of stellar emission tells a richer story than any single wavelength alone, making multi-wavelength observations essential for understanding stars in all their complexity, revealing hidden layers, unseen structures, and processes that would be invisible if astronomers only looked in one part of the spectrum. Making the electromagnetic spectrum a tool for seeing stars in all their dimensions, stars can seed galaxies with heavy elements. Every generation of stars enriches the interstellar medium with heavy elements, created through nuclear synthesis and dispersed by stellar winds and supernovae. Over billions of years, this process has transformed the galaxy from a hydrogen-helium mix to a chemically complex environment containing all the elements of the periodic table. The metallicity of stars increases over time, with younger stars containing more heavy elements than older stars. This chemical evolution is crucial for the formation of planets and life, as rocky planets require heavy elements, and life as we know it depends on elements like carbon, nitrogen, oxygen, and phosphorus, all created in stars. The galaxy's chemical evolution is not uniform. Different regions have different enrichment histories, and some stars have unusual compositions due to specific nucleosynthesis events. Tracing the buildup of heavy elements over time reveals the history of star formation and stellar death in the galaxy, showing how the raw materials for planets and life were gradually assembled, scattered by dying stars, mixed into the interstellar medium, and incorporated into new stars and planets, making every atom in your body a product of this long process. A legacy of stellar nucleosynthesis spanning billions of years, connecting you to the stars that died before the sun was born. Stars can be modelled with computers. Modern astrophysics relies heavily on computer simulations to model stellar structure, evolution, and interactions. These simulations solve complex equations describing the physics of stellar interiors, including gravity, pressure, energy transport, and nuclear reactions, tracking how stars change over time. Stellar evolution codes can follow a star from formation to death, predicting its luminosity, temperature, radius, and composition at every stage. Simulations of binary interactions model mass transfer, tidal effects, and mergers, revealing outcomes difficult to predict analytically. Simulations of star formation model the collapse of gas clouds, the formation of protostars, and the development of planetary systems. By comparing simulations to observations, astronomers test and refine their understanding of stellar physics, identifying discrepancies that point to missing physics or incorrect assumptions. Simulations have become an essential tool, allowing astronomers to explore scenarios impossible to observe directly, to test theories, and to interpret observations. They transform abstract equations into visual dynamic models, making the processes of stellar evolution tangible and comprehensible, turning mathematics into movies of stars being born, living and dying, making the invisible visible, the abstract concrete and the complex understandable, bridging the gap between theory and observation, between equations and stars. Stars can be part of galactic archaeology. By studying the oldest stars in the galaxy, astronomers can reconstruct the early history of the Milky Way, a field called galactic archaeology. These ancient stars, found in the halo and in globular clusters, formed when the galaxy was young, and their compositions, motions, and distributions reveal how the galaxy assembled from smaller building blocks. Some stars in the halo have compositions suggesting they formed in dwarf galaxies that were later consumed by the Milky Way, while others formed in the Milky Way's own early star-forming regions. By mapping the properties of these stars, astronomers can identify the remnants of ancient merger events, trace the growth of the galaxy over time, and understand the processes that shaped its current structure. Galactic archaeology treats stars as fossils, relics of the past that carry information about conditions billions of years ago. And by studying these fossils, astronomers can piece together the galaxy's history, much as paleontologists reconstruct the history of life on Earth from fossils. Each ancient star is a clue, its composition a message from the early galaxy, and together they tell the story of how the Milky Way became what it is today, a narrative of growth, mergers, and transformation, written in the properties of stars that have survived for eons, witnesses to the galaxy's entire existence. Stars can influence galactic dynamics. Stars contribute to the overall gravitational potential of galaxies, shaping the orbits of other stars and the distribution of gas. In the inner regions of galaxies, where stars are densely packed, their collective gravity dominates, creating a smooth potential that guides stellar orbits. In the outer regions, dark matter dominates, but stars still contribute. The motions of stars, averaged over many stars, reveal the galaxy's mass distribution, including the dark matter halo. Stellar dynamics, the study of how stars move under gravity, is a key tool for understanding galactic structure. By measuring the velocities of stars at different locations, astronomers can infer the galaxy's gravitational potential and the distribution of visible and dark matter. Stars also affect the galaxy's evolution through feedback, the energy and momentum they inject into the interstellar medium through winds and supernovae, which can heat and expel gas, regulating star formation. In this way, stars are not just passive inhabitants of galaxies, but active participants in galactic evolution, shaping the galaxy's structure, dynamics, and star formation history, making the galaxy a complex self-regulating system where stars, gas, and dark matter interact, each influencing the others, creating the observed properties of galaxies through billions of years of coevolution, a dance of matter and energy on the larger scales. And so, our quiet journey through the stars comes to a gentle close. We've travelled far tonight, from the birth of stars in cold molecular clouds to their deaths in supernovae and beyond, touching on questions that span the entire life cycle of stars, the formation of elements, the creation of planetary systems, and the role of stars in the larger cosmos. The theories behind us now, like stars fading into dawn, each one a small light in the vast darkness of what we don't yet know. Some theories offered answers, others only deeper questions. Some felt solid, grounded in observation and mathematics. Others shimmered like mirages, speculative and uncertain. But all of them carried a piece of humanity's endless curiosity, our refusal to accept the universe at face value, our need to wonder and question and reach beyond what we can see with our eyes alone. These theories, some ancient and some born yesterday, represent our attempts to understand the stars, those distant suns that have watched over Earth since long before humans existed, that will continue shining long after we're gone. Theories are strange things, aren't they? They're not quite facts, not quite fantasies. They live in the space between what we know and what we imagine, between observation and speculation, between data and dreams. They're humanity's way of reaching toward truth with imperfect hands, building bridges across chasms of ignorance with materials we're still learning to work with. Some theories will be proven right, confirmed by observations and experiments, becoming part of the solid foundation of knowledge. Others will fade, replaced by better ideas, more complete explanations, deeper understanding. But the reaching itself, the wondering, never stops. Each generation of astronomers builds on the work of the last, refining theories, making new observations, asking new questions, and the process continues. An endless quest to understand the stars and, through them, the universe itself. If your eyes are already heavy, that's just fine. Perfect, even. Let the last traces of stellar theories fade behind your thoughts, becoming less distinct, less important. Images of stars and nebulae and cosmic cycles dissolving into the general darkness behind your eyelids. Let your breath carry you softly into rest, each exhale releasing a little more tension, a little more of the day's weight, each inhale drawing you deeper into calm, into the quiet space where thoughts slow and sleep begins. There's still so much more to discover about stars, endless theories waiting, new observations being made every night by telescopes around the world and in space. But for now, you've learned enough. You've wondered enough. You've travelled far through mysteries and questions, and the stars can wait until morning, patient and unchanging, ready whenever you return to look up at the night sky and wonder again. You don't need to remember any of this. Not the names of stars, not the details of fusion reactions, not even the theories themselves, their mechanisms and implications. They were never meant to be memorized, only experienced, like watching stars drift across the sky on a clear night, beautiful in the moment, not requiring retention or analysis. What matters is not what you retain, but how you felt while listening. The gentle stimulation of curiosity, the mind engaged but not stressed, learning without pressure, the soft pleasure of learning something new, of encountering ideas that expand your sense of what's possible, what's real, what might be true. The quiet comfort of questions asked in darkness, theories presented not as demands for understanding but as invitations to wonder, as companions for the journey towards sleep. That's enough. That's everything. The theories themselves will fade, but the feeling of peaceful curiosity, of wonder without anxiety, of learning as a form of rest that can remain. A gift the stars give freely to anyone who looks up and asks why, how, what if. Notice how your body has grown heavier as we've talked, how your muscles have softened, tension draining away like water seeping into sand, how even the weight of your thoughts has decreased, the mental activity that was so busy earlier now slowing, quieting, like a wind dying down at sunset. This is the natural rhythm of rest, the way consciousness gradually releases its grip, letting you drift from waking into that liminal space between waking and sleeping, and eventually into sleep itself, deep and restorative. You don't need to force it. You don't need to try to sleep, to make it happen through effort or will. Just allow it, the way you'd allow yourself to float in calm water, trusting the water to hold you, trusting buoyancy and physics to keep you safe, trusting the darkness to be safe, not threatening but welcoming, a place of rest and renewal, where the mind can wander freely or rest completely, where dreams can come or not, where you can simply be, without tasks or responsibilities, without questions that need answers, without anything required of you except to rest, to sleep, to let the day end and tomorrow wait until it arrives. There's nothing you need to do now, no answers to chase, no puzzles to solve, no theories to understand or remember. The stars will continue their slow dance through the galaxy, whether you think about them or not. Fusion reactions proceeding in stellar cores, light streaming across space, planets orbiting, nebulae glowing, the cosmic cycle continuing without pause, without needing your attention or understanding. The universe is patient. It has been here for nearly 14 billion years and will continue for trillions more, and it does not require your wakefulness, your comprehension, your engagement. It simply is, vast and ancient and ongoing, and you can rest within it. A small consciousness in an enormous cosmos, connected to the stars through the atoms in your body, through the light that reaches your eyes, through the shared physics that governs both stars and cells, but free to sleep, to dream, to let go of everything except the gentle pull of sleep, the soft descent into unconsciousness, the natural and necessary rest that every living thing requires, that you deserve, that awaits you now just beyond the edge of waking, in the quiet darkness where sleep lives. Thank you for spending this time with me, for letting me guide you through these theories, these questions, these mysteries of stars and their secrets. Thank you for your curiosity, for your willingness to wonder even as sleep approached, for choosing to end your day with learning rather than emptiness, with questions rather than silence, with the gentle engagement of ideas about stars, those distant suns that have fascinated humans since we first looked up and saw points of light in the darkness and wondered what they were. It means something, this choice you've made. It says something about who you are, someone who seeks understanding even in the quiet moments before sleep, someone who finds peace in learning, who can be curious and restful at the same time, who values knowledge not just as a tool but as a companion, something to keep you company as you drift towards sleep. And I'm grateful to be part of your evening, part of your routine, part of the quiet ritual that carries you from waking into sleep, a voice in the darkness talking about stars, about theories, about the universe's mysteries, hoping to make your journey to sleep a little more interesting, a little more peaceful, a little more connected to the vast cosmos beyond your window. You're not alone in this, you know. Right now, all across the world, others are listening too, drifting through these same theories, wondering these same questions about stars, about fusion and supernovae and habitable zones and the cosmic cycle of matter. Some are ahead of you, already deep in dreams, the theories having carried them to sleep minutes or hours ago. Others are just beginning, their day ending as yours is, seeking the same peaceful transition from waking to sleeping, the same gentle engagement with ideas that don't demand too much, but offer enough to occupy the mind without stressing it. But you're all connected by this shared experience, this common journey through mystery and wonder, through theories about stars that shine in the night sky, distant and ancient and beautiful. A quiet community of curious minds, seeking rest and knowledge in the same breath, finding peace in questions that have no final answers, in theories that remain uncertain, in the vast unknowns that surround even our best understanding of stars. You're part of something larger, this moment, this listening, this drift towards sleep accompanied by thoughts of stars and space and cosmic time. Imagine yourself now, floating through the theories we've explored, passing by them as if through constellations in the night sky, each theory a star, some bright and clear, others dim and distant, all of them arranged in patterns that tell stories, that connect ideas, that map the landscape of human understanding about stars. Questions above, questions below, a galaxy of wonder all around you, and you at the quiet centre, resting in the knowledge that mystery is not something to fear, not a failure of understanding or a gap that must be filled, but something to embrace, to appreciate, to find comfort in. That not knowing is not failure but invitation, an open door to curiosity, to continued exploration, to the endless human project of trying to understand the universe we find ourselves in. That the universe keeps secrets not to frustrate us, not to mock our ignorance, but to keep us curious, to keep us reaching, to keep us human in our wondering, in our questions, in our theories that try to bridge the gap between what we observe and what we understand. Let that thought comfort you now as you drift towards sleep. Let it wrap around you like a blanket woven from starlight and uncertainty, soft and strange and somehow perfect, a covering that keeps you warm not through answers but through questions, not through certainty but through wonder. The theories we have explored tonight are just whispers in an infinite conversation, questions asked across time, mysteries that connect us to every human who has ever looked up at the stars and wondered, from ancient astronomers tracking planets to modern astrophysicists modelling stellar evolution, all asking the same fundamental questions. What are stars? How do they work? Where do they come from? Where do they go? And what does it all mean? You're part of that long conversation now, having listened to theories, having wondered about stars, having connected, however briefly, to the cosmic questions that have fascinated humanity for millennia. There's nothing left to do now. No answers to chase through the darkness, no puzzles to solve before sleep, no theories to understand completely or remember perfectly. Just the calm certainty that mystery itself is a kind of lullaby, one that will carry you into sleep if you let it, if you stop trying to understand and simply allow yourself to drift, to float on the surface of wonder without diving deep, without needing to reach the bottom, without requiring resolution or closure or answers. So let go now. Let your mind wander where it will, through dreams of stars and galaxies, through memories of nights spent looking up at the sky, through darkness or nothing at all, whatever comes naturally, whatever your mind chooses to do in this liminal space between waking and sleeping. Let your consciousness dim like a sunset, gradually, naturally, beautifully, colours fading from bright to soft to dark, light giving way to night, awareness giving way to sleep. And know that when you wake, the theories will still be here, the questions will still wait, and the universe will still be strange and wonderful, full of mysteries and marvels, stars shining in the darkness, waiting for you to look up and wonder again. I hope you sleep well and dream softly. May your rest be deep and untroubled, your dreams gentle and pleasant, and your tomorrow bright with possibility. Thank you for being here, for listening, for wondering, for letting these theories about stars carry you towards sleep. Good night.